Okay, get this. An air filter that doesn't need to be plugged in. A device that doesn't just scrub pollution out of the air, but actually eats it and uses it for power. It sounds like something straight out of science fiction, right? Well, it's a very real concept, and we're going to break it down today.
So let's start with a really big question. We all think of pollution as waste. It's this nasty stuff we have to get rid of. But what if we've been looking at it all wrong? What if we could just flip the entire script and turn this problem into a solution, this liability into a resource?
I mean, think about any regular air filter. It's totally a one-way street, right? It traps all the gunk, but then what? You're stuck with a dirty filter you have to clean or just throw out, which, just creates more waste. This new idea completely breaks that cycle. It's a filter that actually feeds on the pollution it collects, turning that waste into the very electricity it needs to keep running.
So what is this thing called? The official name is the Unified Multi-Cell Cartridge, or just UMC for short. And the concept is just brilliant. It's a smart dust filter, but the whole point is for it to be completely self-sufficient, generating its own power from the very mess it's designed to clean up.
So how in the world does it pull this off? Well, let's just follow a single dust particle on its little journey through the system. First, the dirty air gets sucked in. As the dust gets trapped, it gets a little zap, and that creates an instant jolt of electricity. Then all that collected dust gets digested over time, which makes a slow, steady trickle of power. And the final outputs? Clean air and a totally self-powered device. Pretty cool. All right, so that's the big picture. Now let's get into the nitty-gritty. How does it actually work? The whole system is built around three main parts, or cells, and each one has a really specific job. This is where the magic really happens.
First stop for our dust particle is cell A, the static shock engine. Now, think about when you rub a balloon on your hair and it creates static electricity. This cell does something kind of like that, but way more advanced. As the air and dust rush through, the friction generates a spark. This creates these really quick, powerful spikes of energy, and at the exact same time, it traps the dust. The tech is called a triboelectric nanogenerator, and it's basically doing two jobs at once, filtering and making instant power. So after getting zapped and captured, the dust falls into cell B, the collection chamber. And this is where the biology kicks in. Inside this chamber, there's some helpful white rot fungi, and they just get to work, pre-digesting all that solid pollution. They're essentially breaking it all down into a stable, energy-rich liquid, almost like they're making a fuel smoothie for the next stage. That smoothie then gets sent over to cell C, which is basically a mechanical stomach. This cell feeds that liquid fuel to special microbes. And as these tiny little organisms eat the pollutants, they release electrons. That process creates a slow but incredibly steady flow of electricity. It's called a microbial fuel cell, or MFC. Think of it as a tiny biological power plant inside a box.
So this is the really crucial part to get. The system has two totally different ways of making power. You've got the tang in cell A, which is like a lightning strike. Bam! A huge, powerful burst of energy that's over in milliseconds. And then you have the MFC in cell C, which is more like a steady water wheel, just producing a small, continuous trickle of power over hours or even days.
Of course, you can't run a stable system on just lightning strikes and slow trickles, right? You need a smooth, reliable power source. And that's the job of the energy mediator. It's a supercapacitor, and it basically acts like a power manager. It stores those big bursts from cell A and that steady flow from cell C, and then it blends them together to provide a nice, smooth stream of electricity to run everything.
Okay, so the science is incredibly cool, for sure. But is it actually practical? Well, this isn't just a theory on a whiteboard. The design has a clear path from just a clever idea to a viable, real-world plan, with specific performance and safety goals built right in from the start.
First things first, a filter has to, filter, and this design sets the bar really high. The target is to capture at least 95% of those really dangerous fine dust particles, the ones we call PM2.5. For any air filter, that is a seriously impressive goal.
And here it is, the main event, complete energy independence. This system is designed to run for over 72 hours, that's 3 full days, entirely on the power it generates all by itself. This is what makes it a game changer for remote places or off-grid sensors where you just can't count on a steady power supply.
And of course, anytime you're dealing with high voltage, safety has to be priority number one. Some electronic air cleaners can actually produce harmful ozone as a byproduct, so this design tackles that problem head-on. It has a built-in safety gate that makes sure ozone levels never ever go above a strict limit of 20 parts per billion. If it ever gets close, the system just shuts down. And like I said, this isn't just a concept on paper. There is a clear, step-by-step plan to bring this thing to life. This 120-day timeline maps out the whole path to a working prototype, from the first power tests to getting the biological parts stable, and then finally putting it all together for some real-world stress tests.
When you boil it all down, it just comes back to this incredibly powerful shift in how we think. The core idea is simple. We stop treating pollution like a liability, something that costs us time and money to get rid of, and instead, we start seeing it as a resource, something that we can actually harvest.
And that leaves us with one last, really big question to think about. This single filter is designed for one specific spot, like on a smokestack or in an air duct. But what happens if you scale it up? If just one of these smart filters can power itself just by cleaning the air, what could 1,000,000 of them do for our cities? What kind of world could we build if our own infrastructure didn't just consume energy, but actually created it from the very air we need to breathe?